So we are happy to have Swarnava Mukhopadhyay from TIFR. So he will talk about combinatorial structures in the moduli space of vector bundles.
Okay, so thank you, Venkatesh, Professor Chari, and Raghavan, who is probably not here, for giving me the opportunity to speak in this wonderful event. Yeah, so actually I have met Professor Lakshmibai once during my undergraduate in Chennai. As Rajan was saying, that she used to come to Chennai every year. Okay, so yeah, I want to speak on this topic of combinatorial structures in the moduli space, mostly like arising out of the moduli space of vector bundles on curves being smooth projective curves. And this is a joint work with two of my collaborators, Peter Littelmann in Utrecht and Sergei Galkin in PUC Rio. Okay, so let me introduce some of the main players. So throughout this talk, so there will be like, as a topic of the conference is geometry, representation theory, and combinatorics. I think I'll try to justify all those topics. Yeah, so the main player in this thing is the moduli space of vector bundles of fixed determinants. So C is a smooth projective curve. Epsilon is the parity of the degree of the line bundle that you are fixing, and 2 is the rank of the vector bundle. So this is the moduli. This is the thing. So it's a Fano variety, which means the canonical bundle is anti-ample. And yeah, so using this thing, so we want to study this space and algebraic geometry. We want to study the sections, space of sections. So those space of sections of a canonical line bundle, which is known as the theta line bundle, is known as the space of conformal blocks. More on space of conformal blocks you will see in Tanmay Deshpande's talk tomorrow. And then there are also these parabolic analogs which we used to construct degenerations. And the degenerations I want to study are toric degenerations of that Fano variety, the Fano variety of rank 2 bundles on a curve. And yeah, so Professor Lakshmibai has a lot of beautiful results on toric degenerations, especially Gonchulia and Lakshmibai, that has been used quite a lot in studying in studying this what's called mirrors for this for some Grassmannians and Schubert varieties. Okay, so I want to study. I want to take that moduli space and degenerate the curve C to basically a chain of P1s, maximally degenerate as much as possible in the moduli space of in the Deligne-Mumford moduli space, and we want to study like how if you degenerate along 2 different paths, the toric varieties you get, how are they related, and that would give me some cluster-like structures. And then finally, if time permits, or maybe I think this will come in the middle, like how do you recover the toric variety from the curve itself? Suppose I give you the curve as some polarization data, how will you get the toric variety back? So the 5th point is like a Torelli type theorem. Okay, so let me some of the main player the character which will be there, but it's kind of not come out directly, is the space of conformal blocks. So which I'm just only going to define in genus 0. So I've given a genus C definition earlier, just the space of sections of line bundles on these moduli spaces. So they can be constructed using representation theory. And in genus 0, so you can think of them as like some refined invariants. So this is the space of invariants of tensor product of representations. And then I'm going to I'm going to look at a subspace on which this operator acts trivially. Okay, so this operator x theta is a generator of the theta root space. So theta is the highest root, and this operator is of course nilpotent because x theta acts nilpotently. So in particular, if I make L to be very large, then these 2 spaces coincide because basically I'm not doing anything because this operator is nilpotent. Okay, so this space depends upon these points and also on the level L. So this is the main point. So you can think of these n distinct points as n points on P1, and you're thinking like as those, and this is like as these points moves in the moduli space of genus 0 curves, this kind of forms a vector bundle. Okay, so this is the main player. So all you need to remember is that it's a refined invariant that depends upon L, and if you take that L to be very large, you get the space back. And then so there's a very specific description, and I'm not going to go anything beyond G equal to SL2 today. If I take G equal to SL2, you're basically looking at invariant forms on these symmetric powers. So as we know, these are the irreducible representations of SL2. This first condition is required For non-zeroness, the first two conditions. So this is like the even condition, and this is called the triangle inequality for this invariance to exist. And this is the perimeter inequality. So this is the inequality that will determine the conformal blocks. So if you have these two, so the space of SL2 invariance is always dimension 1 or 0. So the conformal blocks is dimension 1 if this condition is satisfied and 0 otherwise. So these are very common. These are very popular identities. These are known as Clebsch-Jordan identities, and this we have seen like one of the fundamental identities that coming out of representation theory, and we will this will show up manifestly in what I talk about. So yeah, so triangle plus perimeter. So this is what conformal blocks are in genus. Okay, so let me motivate why I'm interested in toric degenerations, or why people are interested in toric degenerations of Fano varieties. So if you're not aware of this, just ignore it, but I'll just explain the problem. So I'm interested in counting some invariants, some symplectic invariants. So for that, I look at the moduli space, conservation moduli space of stable maps. So basically, these are maps from rational curves to X. X is a smooth Fano manifold, Fano variety. And I have some mark points. And using those mark points, I can form an evaluation map. Basically, a point here looks like a point in the moduli space is like this. You can just basically evaluate. And on this moduli space, you have some line bundles. Basically, you have this curve, and you look at the cotangent. This is what's called a psi class. And here I'm fixing on the integer z, basically just the pullback of the canonical. So you're fixing m, you're fixing the number of mark points k, and you're fixing the variety. And then you're looking at this moduli space, which is xmk. So this moduli space is where the Gromov-Witten theory takes place. This is the conservation moduli space. Yeah, so I'm interested in this number. So this is known as the descendant Gromov-Witten numbers. Okay, so this m and this thing is chosen such that the dimension is 0. So the codimension of these classes is 0. So this is actually a number that makes sense. And so the question is, what people are interested in is to compute this number. So you don't want to compute them individually, but often you can get it in a package. So essentially, the question is, can we compute this generating series? This is the problem that motivated all this toric degeneration work. And then, so this is what's called these are what are called mirror potentials. So basically, the question is, to answer that question, the question one people are interested in is that you construct a Laurent polynomial. You can think of it as a map from the dimension, the dimension x dimensional torus. So this is basically a Laurent polynomial once you choose a basis of the torus, and then such that this equality holds. Okay, and then actually, this is not very efficient computation wise. Also, like you need to find a efficient way to compute it, because if you just take a Laurent polynomial in say like 10 variables with like 4 terms, like say 20 terms, and then if you want to compute these PMs, its computation is not good if you just do the usual algorithm. Yeah. So Laurent, it's a Laurent polynomial, not even a series. Yeah, it's a Laurent polynomial. Yeah, it's a polynomial. Yeah. So yeah. Right. So this was kind of came out from the physics side. So Hori, Vafa, Giventhal, they computed this for smooth toric and Fano toric complete intersections. Galkin, Kurtz, Korty, Kasparczyk, they were interested in. So they took this list from Iskowski's classification of Fano three-folds, and then they computed all of this. So this is just the history. And then this paper of Batirev, Chaukan, Fontaine, Kim, Duke of Van Straten, they kind of used works of Lakshmibai and Gonchalia to kind of to prove their results. So today, so there is actually an algorithm that comes from physics, which one tries to follow. But before an algorithm, I just want to give some definition of polytopes. So given a multivariate Laurent polynomial, you just look into the monomials and look into the exponents and look at the convex hull of all the exponents. So this is what's called the Newton polytope of a Laurent polynomial. And you can do the reverse. So if you are given a polytope, you can look at the vertices, use the vertices as exponents, and then take the sum of the monomial. This is what's called a Newton polynomial. And then given a polytope with 0 in the interior, you can of course, take the dual polytope, because a polytope like this will be given by an intersection of facets, and then you just look at the equation of the facets and then take this. So this thing is in the dual lattice, the polar dual. So let me just give you an example. So this is, so this is the P. This is the polytope. If you look at the polar dual, this is just this polytope, and this is the Newton polynomial of P0 is just this, because these are the vertices. So so if you are familiar with some toric varieties, this is it's pretty clear. So this is the moment polytope of P2, and this is the dual polytope of the moment polytope, and this is actually the Laurent polynomial that computes the required Gromov-Witten numbers for P2 that I pointed out. So very simple. So then there's the B side being the algebraic geometric side. There's a paper by Iguchi, Hori, Zhang, and also Giventhal I added, but the paper is by the first three of them. So their algorithm is very simple. You start with a Fano variety, you degenerate it to a toric variety, and you assume that the toric variety has nice singularities. So like the terminal is good. So basically, if you can assume that the moment, the dual of the moment polytope, the lattice, what's called the Newton, the dual of the moment polytope P0, the only lattice points are the origin and the vertices. So they have no non-trivial lattice points. So this actually guarantees that the toric variety has terminal singularities, and then one should take the Newton polynomial of the polytope P0 and then think of this as a function of the dual torus variety. So this is the dual. So Tx0 is a torus acting on x, and Tx hat is the dual torus. So this function W can be thought of a function of the dual torus. So this is what the duality is coming up. And so now this is now a theorem. This is a theorem due to Nishino, Nohara, and Ueda under the assumption that X has small resolution. And along with Bellmans and Galkin, we proved it with the assumption that some assumptions that this that some map, basically some assumption on the Picard group of X. And this combines, so both these results combines works of Tonkonaug and also Bondal and Galkin. So we have an algorithm. So I'm interested in, so that's the goal. So I want, give me a Fano variety, construct a toric degeneration, look at the dual of the moment polytope, and compute the function W, compute the Newton polynomial of that polytope. That's the goal in mind. No, it doesn't. So I'm coming to it. Because at the end, this is supposed to compute a symplectic invariant which doesn't see the degeneration. So they should be equal, right? So that should give me some interesting relation. So that's the cluster-like structures that's coming up. Okay, so this is this is from the original paper. So they were looking into Grassmannian 2.5, and this is what they call the grid. This is the grid graph, and this is what is called the H potential. So for every vertex, I'm just assigning the variable, and to every edge, I assign the variable. So look at the direction, it's a directed graph. Look at the head of the arrow, look at the variable, and then divide it by it. So x11 has nothing coming in, so that's why it was x11. You can think of an empty like array. And then x12 corresponds to this edge, x21 corresponds to this edge, and finally you have x23. So x23 have this two, but then you can think of an empty edge going out of it. So that's why this term. And this q is some q, you can put any value of q. And so their proposal was, so in their experiments they said that this should be the polynomial that counts that Gromov-Witten numbers for this particular Grassmannians. Okay, so this is what Iguchi, Hori, and Zhang did. So this paper called Gravitational Descendants. So this is from that paper. So it only gives you the, I think, part of it, not the, it probably gives you the part of the I function. So basically look at the Dubrovin manifold, look at the one parameter subgroup given by the power of the canonical class, and you pull back the quantum D module. And this is the solution of the quantum D module. That's what you will get. Okay, so this is the proposal. So I want to do this proposal for the Fano variety that is very popular, at least in this part of the world. Modular space of vector bundles. That's the Fano variety. Okay. So how do you degenerate curves? So as I pointed out, how do you degenerate? Well, first thing to do is that It's a moduli problem, degenerate the curve as much as possible. Okay, so this is what called the C hat is a maximally degenerate curve. That means you cannot degenerate it further in the Deligne-Mumford moduli space. So all components are P1. So basically it's a like a tree of P, like a bunch of P1s, and then and then each component should has at least 3 special points. That's the stability condition. So here is 2 components meeting at 3 points. And assigning to this, I want to assign. So I want to, but you have killed the geometry of the curve. It's just data. So essentially, this is the combinatorial data. So what I'm going to do is that for each component, I'm going to assign 2 vertices, 1 and 2, and 2 vertices are connected by 3 edges. That's kind of recording the fact that they meet at 3 points. Okay, so this A, B, C are the 3 intersection points that corresponds to the 3 edges, and then you have these 2 vertices correspond to the 2 components. Yeah, maybe I should have colored them as well. Yeah, sorry about that. Okay, so in general, if I give you 3 curves, you can think of, if you're a topologist, you can think of them as choosing 3 G minus 3 homologically non-equivalent disjoint circles and cut them so that you get into a pair of pans. So here is a complete picture, which I think it's not due to me, I found it on the internet. So yeah, so it's a disclaimer. So you see, you can take these 3 circles or you can take these 3 circles. So these circles will produce 2 different pair of pans. Right, so in this thing, 2 red circles are together, and here 2 yellow circles are together, but here this thing is mixed up. Okay, so this can be again captured by the data of this what I call the dual graph. So basically, a trivalent graph is a graph where each vertex of degree 3, and what you do is that given a pair of pans decomposition. So this is a decomposition of pair of pans because this looks like a pans, like yeah, like the legs and the waist, yeah. Yeah, so given a pair of pans, what you do is that you assign a trinion. Trinion is basically one vertex with 3 things coming out, and then connect the half edges if the pair of pans is obtained by cutting along a circle, and this graph corresponds to the deepest stratum in the moduli space. So let me do an example. So this is the 2 things I have from the previous example, previous thing I did. So I assigned the trinion, right? And this trinion is obtained by cutting the red circle. So you basically join them. And here, this is obtained by cutting the yellow circle, so you join them. And then this is obtained by cutting the blue circle, so you join them. So you get this graph. So this is like looks like dumbbell or like, yeah, or like Gandhiji spectacles. And here, this is obtained a different way. So you have 2 green circles, and you have like 2 yellow circles which are here. So basically you join along this, and you join along this, and you join this. So you get this graph. Okay, so as you see, these various different choices are captured by this combinatorial data of this trivalent graphs. Yeah, and then once you get all these trivalent graphs, basically if you like whenever you see an edge, you just cut it, then you basically get this picture back. Then you can get the pair of pans decomposition back. So this is kind of completely captures the whole data. Okay, so this is a result of Christopher Manon, who wrote down the toric variety about what the toric variety should be if I take the moduli space of bundles of rank 2 with fixed determinant. So I'm losing the L in the notation just because it's irrelevant, because it just depends upon the degree modulo even and odd. So that's why this M0 and MC. And he's giving the toric variety, and the toric variety looks like this. Okay, so as you see in my clip, in the very first towards the beginning, I talked about this Clebsch-Jordan identities. So this is basically the Clebsch-Jordan identities. Like this circle, this looks like the triangle inequalities, and this is like the perimeter. So this shift comes from the fact that we have to remove some tradpoles, and our contribution is that one has to do some Hecke transforms to relate, because if you're looking at a like modular space of rank 2 bundles with a fixed determinant, which is not trivial, that's not a G bundle. So you have to relate it with a parabolic bundle and then do some Hecke transform business to kind of come to the setup of this conformal block or this Manon setup. And that involves like removing, so Manon's story will have some half edges, which we call tadpoles, and it's kind of removing all those tadpoles. Okay, so what goes on in Manon's degeneration? It's kind of important because this is like kind of non-trivial input. Yeah, so what goes on in this degeneration? So this degeneration is fundamentally kind of representation theoretic, okay, and geometric as well. So this is a nice observation. So if you like start with G is a Lie algebra, and you take a tensor product of n finite dimensional modules and look at the invariance, right? And then you choose any m between n and 1, then they have this factorization. Okay, just observe that this thing is infinite, sorry, finite, but the sum is infinite, but only finite number of things shows up. Yeah, because it's going to go to 0 because it doesn't have this. But this is this property called factorization. So this similar property holds for the conformal blocks as well. So let me just not describe everything, but just draw a picture. So if you think of conformal blocks as a functor assigning something to a decorated curve, so you take the curve and then you take the normalization of that curve. Okay, so it's just saying that the original thing is a direct sum of over these conformal blocks on the normalization. And similarly here, so if you have so this is the normalization is disjoint, and so this more looks like the previous example, like the product of conformal blocks. So this is this story. Yeah. So what does the storic degeneration do? So again, you start with the section ring of the modular space of bundles on curves, degenerate the ring. Okay. Now the problem is that if you have a singular curve, the modular space of bundles is not so well behaved. I mean, the stack is well behaved, but it's very hard to define it, the semi-stability conditions and so on. So that's why it's much better to do it on the level of these conformal blocks, which are actually constructed using representations of the affine Moody algebras. So from there, this factorization theorem works. But I think even in SL2, I guess the factorization theorem, the geometric setup was also proved by Ramadas and Narasimhan, and probably recently Sun might have generalized it to type A. But for arbitrary types, these results exist. So now you have degenerate the curve C to C0, and then that will degenerate the ring, which can be constructed in representation theory to, sorry, there's a spelling mistake. So degeneration of RC to the section ring R par of parabolic bundles of rank 2 on the normalization. So as I pointed out that you go to C0, which is a very degenerate curve, you have to look at the normalization. So then it's just a bunch of P1s with 3 mark points. So you look at parabolic bundles on that, and parabolic bundles on that space can be controlled. Yeah. So this looks like, again, tensor products of invariance because on P1, as I pointed out, I defined conformal blocks as refinement of invariance, right? So this all goes in. So let me tell you how this thing is. So you start with a genus 3 curve, and then you cut it like along these circles. So then you get this, and then you disjoint all the edges, right? So this is the graph corresponding to the nodal curve, like maximally degenerate curve, and then you look at the normalization. This is the data of the normalization. It's a bunch of P1, and these things corresponds to 3 mark points. So what Manon proves is that this algebra of conformal blocks on this nodal curve, on this thing, can be related to this algebra where RV is the algebra of conformal blocks on P1 with 3 mark points. So the refined invariant satisfying this can be given by these Clebsch-Jordan identities. And then in this graph you have like too many components, right? So there are like 4 components, right? So this factor corresponds to the vertices. But you need to identify, right? You need to remember that this graph came from joining them, right? So they have this so on this half edges they have the weights. So you have to make sure that the weights on this thing and the weight on this thing agree, right? Because in the factorization theorem, I have this result, right? This mu and mu dual. So if you start with a conformal block or invariance where you have some alpha here and you have beta here, you cannot join them. You can only join alpha and beta if they are like beta equal to alpha dual. So to take care of that, we have this torus. So you can, if you want to think of it geometrically, you can think of it as the gluing data for the bundle. So if you want to define a bundle on a nodal curve, you define it on the normalization, and then you look at the clutching functions because you are going to identify 2 points. So this is what it is. And then RV is related to tensor product of SL2 representations as described earlier using the Clebsch-Jordan identity. So there is no problem in defining my degeneration. So I've kind of reduced myself to the 3-point case, and then the 3-point case in SL2 is especially easy. So in other groups, this is not so easy because in other groups, representations have multiplicities, even 3 points. And so conformal blocks could be not either 1 or 0, it could be like pretty non-trivial. So the fusion, that's kind of captured in the fusion ring, and that fusion ring is a non-trivial ring to study. for other groups. But for SL2, things are very simple. And in SL3 also, this can be carried on. So basically, that's how the degeneration kind of is constructed. Basically, you start with a curve, you degenerate nodal, and then you go to this algebra where you have like a P1 with 3 points, and the 3-point case can be handled by Clebsch-Jordan identities. And that's why you have all these polytopes. And as you see in this equation, in the polytope equation, you have like this thing for every vertex. So that's why. So this is the Clebsch-Jordan and the perimeter. Okay, so this is the corollary that we prove. This is a theorem that we prove that the variety that you obtain by degenerating in this way has terminal singularities. That means the lattice polytopes or the lattice points of the polar dual of the moment polytope are just the origin and the vertices. And this is not always true. This is only true if the graph has no separating edges. So for example, if you look at the Dumbbell graph, it's not true. You can actually, this variety is basically intersection of two quadrics and you degenerate the quadrics. But this one has no non-separating edges, and you can show that you can actually study by hand essentially. Like, yeah, very explicit. Okay, so the corollary is the following: that if gamma be a trivalent graph of genus G, with no separating edges and one colored vertex, then W gamma TC is a Newton polynomial of the fan polytope of XT, and then actually this gamma TC computes the quantum periods of MC, and that's the earlier theorem I mentioned, the proof of the proposal. Yeah, so you might be wondering what this C is. The C is basically doesn't matter what. So C is like coloring of the vertex. So colored either by black or white, so this kind of is taking the total number of colored vertices corresponds to the degree of the line bundle that you have fixed to define the moduli space. So everything should be true on the, yeah. Okay, so we have this theorem that I mentioned as 0.5, the Torelli theorem, which says that, this is a very classical theorem saying that if you have Jacobian and the theta divisor, if two Jacobians are isomorphic to each other as polarized abelian varieties, then the curve should be isomorphic. And similar thing holds also for the moduli of semi-stable vector bundles and in general principle G bundles, that if some space is isomorphic to this moduli space of stable vector bundles, then it has to be, then yeah, you can identify the curve. This determines the isomorphism class of the curve. So we have this theorem that's saying that if gamma C be as above, meaning that trivalent colored graph, and as above with no separating edges, then the toric varieties are isomorphic if and only if the graphs are isomorphic, and not only the graphs are isomorphic, but the coloring, you can think of it as a one cosine, or define a class in the zeroth homology, and that should map to the class of C. So this is like kind of taking care of the polarization data in this theorem. So this is actually a completely combinatorial proof. So this is funny because if you look at the complete moduli space, so for smooth curves we have a Torelli, and for the most degenerate curve we have a Torelli, like this Torelli. So it's an important question that what happens in the intermediate curves. And yeah, I think nobody has studied that, but yeah, it's a good question to study. Yeah, okay, so right. So now that we have the so now that we have this potential for gamma, so we're going to call the graph potential, the one obtained by toric degeneration. I'll give you a formula. So I want to so the original goal is to compute this generating function of the quantum periods, so the periods. So I want to compute this generating series, or sometimes because this is not convergent, I want to compute this. Okay, so question is how to effectively compute this. Okay, so observe that by definition this thing can be written as an integral. Okay, and so you want to say that okay, we want to compare these two functions given by two different toric degenerations, and since they are an integral, you can think that okay, two integrals are the same. If I do a change of variable, that preserves the volume form. So that's kind of the starting point. Okay, so this is the function that we are considering the function on the Newton polytope of the toric degeneration. So what we do is that so this is the tranion, so that I assign to a pair of pairs. You basically take this function, and there's a colored version. So basically, you just take like the invert everything. So basically, the coloring is like taking one variable and replacing it by its inverse. If I take x here and replace x by x inverse, I get this. And if you take two variables, you don't do anything. If you take three variables, you kind of move back and forth. So this is always this mod 2 thing of the coloring. Okay, and then this is the definition of the potential that we found, that basically to that graph that defines the toric degeneration, you assign this. So for every vertex, you had this vertex potential, and then you sum over all vertices. Let me give you an example. So here is an example. So you have this graph is called a theta graph. So on the left vertex, you have these variables, and on the right vertex, you have these variables because this thing is colored, and then you add up. Similarly, in here, you have this. So there is this 2 coming because of the fact that B and C are equal here, because there's a loop, right? So if I cut it, the loop looks like B comma B, and here the loop looks like C comma C. That's why these multiplicities come out. So in some sense, I already told you that this graph is bad for geometry, and the reason this is bad is because of these coefficients. Yeah. Okay. So this is a genus 3 example. So basically, you have these vertices, and you basically do it. So basically, take a magnifying glass, look at it locally. Then locally, they are like these ADF variables. You just do it. Then you do it here. So C. So this is a colored one. So that's why 1 over C. Okay. So what surprise? I mean, not surprising, but it should be expected that this expression should be the same, because they are computing something. But how do you prove that these are the same? So it turns out to be this for this genus 2. So this was the starting point of our investigation. How to show that independently that these 2 things agree. We know that they should agree, but how to show this is independent? Okay, so in particular, that's sorry. Yeah, right. Okay, so this is what we prove. So if you take this necklace graph, okay, so this is a genus G graph, which is a very inductive structure, and then then you consider this Bessel function, and then you consider this function T1, which is just like modification of the Bessel function, and this is the theorem that we prove, that if you look at the Hilbert-Schmidt operator given by this, so this is a trace class, this is a Hilbert-Schmidt operator in the L2 of S1. So think of x and y as the variable that you use for Fourier transformations, and then you take this S operator, which is just taking xn to xn. So this product of these 2 operators, A and S, they are trace class, and A is a trace class operator. So you can take multiply and then take trace of it. So this makes sense. It will produce you a number, and this is the function that we have. So in particular, what I'm saying is that on the left hand side, doesn't matter what graph you take, but the right hand side is independent of the graph. Yeah, that's what is expected, and this is the concrete formula. So this is a very efficient formula. You can put it in your computer and generate it to like many genus, and then try to understand. And we actually proved some identities combinatorially that we couldn't have guessed earlier. For example, one of the things that one can show is that some particular number up to some multiple, some particular number for the modular space with fixed determinant of odd degree is related to the modular space of fixed determinant of even degree, and that's kind of not expected. Yeah, and somehow we could see this by using our formulas. Anyways, so this is the starting point. So one can ask why does the left hand side is independent of gamma? So we know that it will be independent of gamma, but how do we actually prove it? Okay, so prove it like without using the mirror, the fact that they are the mirrors. Okay, so look at this thing. So if you have a sphere with four punctures, there is 2 ways to decompose it as a pair of pans. You can either cut it here or cut it here, right? So the corresponding dual graph will look like this. So I and j here will be on one side connected to the same vertex, whereas in here I and j will be connected to different vertices. Okay, so this is the basic transformation. So for example, in here also, so here as you see, so these square boxes are the rest of the graph, and this is where the mutation has happened. So A and B are connected to V1, but here A and B are connected to different things. So this is what is called a basic mutation, or you can call it the Hatchett-Thurston move. And then one can show that if you have 2 trivalent graphs, you can go from one to the other by propagating these moves. Okay. So in particular, if I can control what happens to the function around these moves, I'm good. Okay. So instead of looking at the entire function, I just look into the entire graph potential, this W comma mu's. I only look at the part where things are mutated, like just focus on the part with these variables. So this is like 5 variables, and on these 5 variables, because in here nothing will change. Everything will remain the same. So so this is the one. Just as you see, this is with the vertex v1 and vertex v2. I'm just taking the middle variable common, and then look at these forms. Okay, so define these things u, mu, and mu, mu and nu, and then w mu, w gamma mutations look like mu over x and nu x. So this is of this form, and similarly, if you can look into the next one, you get a similar expression, but with mu prime and nu prime. Now, what I want you to observe is that if you take their product, so what has happened between mu and mu prime, and nu prime, right? So this factor is common, but one of the factors have changed. So one of the factors got exchanged. So in here, AC plus BD is there, but here AC plus BD is in the second factor. So what I want you to observe is that if you take their product, they are the same, mu and nu prime. So using this, so basically, so using this, one can prove the following, that they are related by a rational change of coordinates, and the rational change of coordinates that you do is just take z as nu x, put it here, and then again change z by mu prime z prime, and then use the relation to get the thing. So this is a very nice form. So you can think of this as 2 Laurent monomials equal to sum of 2 Laurent monomials. Okay, so if you look at the Floquet relations, the Floquet relations are not like this. Floquet relations are sum of 1 monomial is equal to sum of 2 monomials. Okay, so right, and so corollary that we have is that we have a function from the union of all these toruses, and this torus is identified by this birational change of coordinates, and then you have a function. So this is like in cluster theory, this is like the upper cluster variety, but it's actually not. This is not the full mirror. So it's only an open part of the mirror of this in the sense of homological mirror symmetry. Because what happens is that the critical if you look at the critical points of this function w, one of the things in one of the LG models, what they call in homological mirror symmetry, should be the fact that the inverse image of the critical values should be compact. But here, of course, they're not compact. So this is not a log Calabi-Yau yet, but it's kind of towards the log Calabi-Yau. Okay, so yeah, so for the rest of the talk, so this is like a cluster-like variety, well, this is like the cluster-like transformation, but this is not the cluster algebra, because in here we don't have a quiver, we don't have the directions of the mutations, and so on. So this is more in the sense of Galkin. So Galkin, Cruz Morales, and Galkin and Ushnich, they studied something similar. They want to study, like, construct a mirror of P2 by doing these toric degenerations. And what they found was that they said that they found the Markov quiver, but the Markov quiver is not the LG model. That's what they proved. But then you need some more structures than the usual cluster algebras. Yeah. So here we don't know what is going on. So maybe something on maybe it is like kind of controlled by some graphs in the Teichmuller space or some. Yeah, we just absolutely have no idea. But there is something very similar like cluster algebra like mutations, but we kind of don't know what the actual structure is. Maybe there is something. So there's a recent, not recent, like a year back, there's a paper of Alessio Corti who tried to kind of formalize these structures. Yeah, but I think there are a bunch of conjectures. I don't think it's all open. So yeah, I don't know what will be a good kind of formulation of the generalization of the cluster algebra that should kind of take care of these things. Yeah. Okay. So here I want to now relate it to the since I mentioned the Floquet relations, I want to relate it to the Floquet relations, and I want to relate it to other work, and also I want to exploit the fact that the conformal blocks are refined invariants of tensor product representations, and if you take L to be large enough, they coincide. So I want to explore some consequences of that fact. Okay, so here is another important space that people studied. This is what is called the polygon space. Okay, so basically you're looking at the space of you fix a sequence of integers that satisfy sort of a triangle inequality, and then you're looking at the polygon space. Look at mirrors, sorry, not mirrors, spheres of radius that, so that sum is 0, and then you quotient out by SO3. So this, I mean, if you don't, so this is a symplectic manifold that was studied by Goldman and Milson, and there's a theorem of Knudsen and Hobsbawm that shows that this thing is actually related to the GIT quotient of P1 with respect to GL2 and with respect to these parameters. So these have appeared in your talk, it's Sam's talk, right? So yeah, so as I pointed out, and this is exactly the one that kind of has the information about the tensor product of invariance of tensor product of representations. Okay, so fix a convex planar polygon with n sides. It's called the reference polygon, and look at the set of triangulations of the polygon. So that's in one-to-one correspondence to what are called caterpillar trees, so trivalent trees with n leaves, by sending a triangulation to the dual graph. And then what Nishino and Nohara proved that for any triangulation gamma of the polygon, there exists a toric degeneration of MR. Okay, so MR is this polygon space, and actually they recover what is called in symplectic geometry the Kapovich-Milson bending system. Okay, so and then this was carried on further by Nohara and Ueda, and then they studied this potential called the Nohara-Ueda potential. So they also want to construct mirrors of this Landau-Ginzburg mirrors of this space by exploiting not conformal blocks, but exploiting by looking into it as GR2n and some equivariance with respect to U1 of n. Okay, so what they do is that so if you have a triangle, okay, you can look at the dual graph. So basically, you attach a vertex and then you like join the half edges going to the cutting out the outer triangle, and then call this Yij, meaning that it's hitting the edge Yj, Yik hitting the edge Yk, and Yjk is hitting this. So his thing is a bit simpler, they're thinking. So he's just saying Yij and look at the corresponding cyclic quotient. So product of 2 divided by 1. So difference between with our thing is that we have a 4-term thing, but their thing is only a 3-term thing. So yeah, so how do I lose a variable? Yeah, okay. Yeah, so this is the potential. So this is for Grassmannian n equal to 4 and so 2, 4. So basically it's triangulation of a rectangle. So this is one triangulation, and you look at the dual graph and you have this function. So here I've just took this middle edge and then gathered the terms together. But as you see, this is like 2 divided by 1, 2 terms divided by 1. So for every vertex, you look at the like the cyclic ratios of take the product, divide by the other one. So I've just gathered the terms together. And then if you take another triangulation by taking the different circle, you get a different tree. So here y12 and y23 are attached to one vertex, and here y12 and y23 are attached to different vertices. So it's the same phenomenon that we have seen earlier. Exactly the same phenomenon, like the mutation of graphs. And then here they have this, okay, and then they write down a rational change of coordinates. Okay, so here again this looks like the Plucker because it looks like one monomial as sum of 2 monomials. Yeah. Okay. Then so one can ask, how do I get this from my stuff? Okay. So here, so I have x, y, z. I do a change of variables. Tau, I introduce a new parameter, and then I go like this. Okay. So if I do this change, then my this potential, the Trinidad potential, this is my original one. And then if I do this change of variables, I go like this. Okay. And then when I take the limit as tau goes to 0, voila, I get this thing back. Okay. So this tau equal to 0 is like 1 over L. So as L goes to infinity, tau goes to 0. So this is that fact that conformal blocks are refined invariants, and as the L grows higher, you get back the invariance back. So this is kind of reflected here. Okay. The same thing if you continue. Yeah. So sorry, some big formulas. So if you do this, you have this. Yeah. So I just did the change of variable, and then as you see, in these formulas, it was just 2 terms here, but here I have 4 terms, right? Because this t to the power 4 comes, and as you see, and this is the rational change of coordinates that one takes. Yeah. So here again, it smells like what I had earlier. So my transformation had 2 monomials equals 2 monomials. So here also it smells the same, right? 2 monomials equals 2 monomials. Okay. Now if you take limit tau equal to 0, you get back the Nohara-Ueda relations. So this is like a deformation of their relations, and No, you just have to look into there and think of one. Yeah. You have to look into that stuff and think of one. This is not given by any like rule or anything. Like, come up with this. Yeah. Yeah. Okay. Yeah. So then Nohara Ueda introduces another change of coordinates. Sorry, this looks a bit complicated. And with these halves, so thing is that these halves can be explained as follows, because the lattice where this polygon thing lives is it's not the full lattice. It's some lattice with some index. And I think this square root gives you a natural basis of that lattice inside the trivial, like the Z model. And then if you look at the Nohara Ueda mutation in this new coordinate, it looks like this. And then if you do a further change of coordinates, you get the Plucker relations back. Okay. So one can do the same here. So if I just follow their algorithm, the one that Nohara Ueda does, I get something like a deformed Plucker relation. So essentially, again, Plucker relations look like, so if I put tau equal to 0, this is the usual Plucker relation, but this is like a deformed one because, you know, in my thing, sum of two monomials should be equal to sum of two monomials. So similar thing holds even in n equal to 5. So this is a triangulation obtained by joining this and joining this. This is the caterpillar. It really looks like a caterpillar now because like three beads, and then you have this, and then here the Nohara Ueda function looks like this. So again, you have y25, y35. These are the full edges. Everything else is half edge. So in y25 you have this thing, and then y35, half of it is counted in y25. So I'm not repeating, but this is the part that's remaining. And then similarly, if you take the other triangulation, so this is one. If you take the other triangulation, you get a different look, as like the caterpillar has moved, right? So they kind of turned his head. Yeah. So this is the function. And as you see, this part remains the same, only transformation has happened in this. So here, so I've tried to point out in color, y25 variable is not there in the second one, and y13 is not there in the second one. So these are the new variables. And then Nohara Ueda takes the transformation of this form, okay, the same transformation that he had, like the Plucker. And then if you take ours, it looks like this. Again, they equate sum of two monomials to sum of two other monomials. And again, if you do another change of coordinates, so this one looks a bit funky, but yeah, again, there's a complete general formula. You will recover something like the Plucker coordinates, and here is exactly the Plucker coordinates that Nohara and Ueda recovers. And then again, basically you have the Plucker relations, but with the deformed, with this factor of 1 plus tau to the power 4. Yeah. So in general, so let me end by the theorem. So the graph potential mutation recovers the cluster structures on the Grassmannian 2n as a limit. Okay. So as we point out in the beginning, the operator Tz is nilpotent. Hence, for L greater than 0, the invariance, the conformal block should be equal. And this is reflected by the fact that this tau is coming there. And geometrically, this is a meaning. So if you look at moduli of parabolic bundles with a stability parameter given by the weights, and if you increase the level, the weights decrease, right? Then the stability parameter vanishes. So then it's just a product of, then it's just a GIT quotient of a product of P1s. And that's why that explains geometrically why the conformal block should be equal to the space of invariance. Because as we saw in Sandstock, the space of invariance kind of looks like sections of line bundles on this GIT quotient. Okay, and finally, Marsh and Reek has constructed the mirror. So basically, tried to match up the proposal of Giventhal, proposal of Iguchi, Hori, and Zhang. So you know, in the very beginning, I wrote this H potential like in terms of xi's. So Marsh and Rees managed to construct this for arbitrary Grassmannian, essentially proving they're part of the mirror. I mean, so and various people have various interpretations of the mirror, but yeah, and so essentially we are able to get back the mirror of Marsh and Reek for the case n equal to 2. So this is again as a corollary of our results. Okay, I think it's a good time to stop. Thank you.
Any questions or comments?
So I wanted to ask if you can say anything about the rank level duality for, say, the Lie-Poitier strange duality, and if these combinatorial structure you can say.
Yeah, no, I don't know, because see, these
Because
things are not there in the see, we don't have the mirror for the any other Lie algebra other than SL2, right? So, but but the rank level duality comes from the duality of the Grassmannian, right?
Yes.
So if you have something, it should be showing up there. But as you see that, again, basically what is rank level duality? Rank level duality, basically you take Grassmannian of R planes inside n plus R and then n inside n plus R, and then basically you look at the cohomology groups, right? And the cohomology groups are isomorphic, and then basically you look at the intersection numbers, and those are tensor product of invariants, and then they are dual. Yeah, so basically, essentially the same thing should hold asymptotically. I mean, you can look at instead of looking into rank level duality, you can ask for the same for the quantum cohomology as well. Yeah, I don't know, but they should do something. But I mean, it's a good question. I have thought about it, but I could not answer it. Yeah. So what does rank level duality do on the mirror side? And I think there is some answer about like going around some loop in the Fukaya category, but yeah, I mean, these are all like stories. I mean, I can tell you later if you want.
Thank you. Very nice talk. I have two questions. The first one is if you compared your mutation to combinatorial mutation of polytopes.
Yeah.
Or the mutations of Laurent phenomenon algebras, if they.
Yeah. So I think it should be more like the mutation of the Laurent. Yeah, but the polytope. Yeah. So to look at I think like ideally what would be like the best scenario. You look at the vertices of the polytope. They're like 8 times G minus 1 vertices, and for every and then you have this other polytope which are the vertices, and then you should have some direction which you mutate like you do for like this clusters thing. But those things are even I think the only thing that's known is for like P2 and some del Pizzo surfaces. So for higher things, I don't know. Yeah, good to know. Yeah.
And then the other thing, in which generality do you know this result that you have deformations of the Nohara-Ueda?
Oh, which one?
So yes.
Oh, this thing. So because our thing is only in rank 2, Nohara-Ueda is only in rank 2. So yeah. So but I think the thing is that this phenomenon about limits covering the conformal, because that holds in all arbitrary Lie algebras. So if you have a degeneration of this moduli space for rank R, which I think is very hard or like not very pleasant, you should recover all the Marsh, Reek, and all the Plucker relations for all these things. So that should be normal. Yeah, that should be there.
Thank you.
In one can try it for SL3. There's a degeneration by Menon.
Any more questions? Okay, if not, let's thank Swarnava.